Now let's talk about the heat transfer in insulation material in this particular lecture under areas of chemical process utilities. Now before we go into the detail of this particular content, let's have a brief outlook that what we covered in the previous lecture. We discussed about the brief history of thermal insulation. We had a brief discussion about the purposes of thermal insulation. We talked about the temperature ranges for insulation application. In this, we discussed about the various type of insulating materials. Apart from this, we discussed about the heat transfer modes like conduction, convection, radiation. Now, in this particular lecture, we are going to cover about the heat transfer aspect through the cylindrical insulating material. We will discuss about the heat transfer through spherical insulating materials. We will discuss about the critical thickness of insulation, especially for cylinder and for spheres. So let's talk about the heat transfer in cylindrical insulating material. Now cylinders, they are very common in the chemical engineering operation. So let us consider a long cylinder of length L. Now inside radius is R1 and outside radius is R0, and it is you can see this is a side view and this is the front view of this one. This is the R0, Ri, and the total radius is R. Now this is the differential radius, a small amount of radius. Now cylinder is exposed to the temperature difference of Ti to T0. The length of the cylinder is very large compared with the diameter of the cylinder. So assume that the heat will flow only in the radial direction. That is the space coordinate R need to specify the system. So the area of heat flow in the cylinder will be AR is equal to 2 pi RL. Now according to the Fourier's law of heat transfer through conduction in small element, this dr will be given as QR is equal to minus Ka AR dt over dr, or it can be written as QR is equal to minus K 2 pi RL, because already we have given this area. So QR is equal to minus K 2 pi RL dt over dr. Now the special boundary conditions will be T is equal to Ti and R is equal to Ri and T is equal to T0 at R is equal to R0. So if we rearrange this particular equation and integrate it from T1 to Ti to T0, we can write this equation with respect to the QR over minus K 2 pi L integration dt from Ti to T0, or it can be represented as this is equal to integration R over dr from Ri to R0. Now after integration, the heat transfer rate in the cylindrical material, this can be found by this particular equation, that is Q is equal to K2 pi L Ti minus T0 over Ln R0 over Ri. Now the thermal resistance in this particular case can be written as RTH is equal to Ln R0 over Ri over K2 pi L. Now this thermal resistance concept can be used for multi-layer cylindrical walls. Now here you see that this is the typical figure of a multi-layer cylindrical wall. Here we are having different layers. Now here if you see that R1, R2, R3, R4. So there are 4 different radius apart from this different materials like A, B and C. So the generic equation can be written as Q is equal to 2 pi L T1 minus T4. This is the T1, the inner temperature, and this one is the T4. This over ln R2 over R1 over Ka plus ln R3 over R2 over Kb plus ln R4 over R3 over Kc. Now these are in the series. If you recall that in previous lecture we have already studied about this one. So the resistance to the first layer, second layer and third layer, and this can be like this. Now let's discuss first problem. Now here a thick wall tube made up of stainless steel with inner diameter of 4 centimeter and outer diameter of 8 centimeter. The thermal conductivity of the stainless steel is 19 watt per meter Kelvin. It is covered with an insulation of a thickness 4 centimeter, and that is K is equal to 0.17 watt per meter Kelvin. The temperature at outside of the insulation is around 200 degrees Celsius. The inside wall of the pipe is maintained at 550 degrees Celsius temperature. Now here you need to calculate the heat loss per unit length of the pipe and tube insulation interface temperature. Now it is given that inner radius of the tube Ri is equal to 2 centimeter, and that is equal to 0.02 meter. The outer radius of the thick wall tube R naught is equal to 4 centimeter, 0.04 meter. Now let's draw the figure. This is R naught and this one is Ri. Now the pipe is covered with 4 centimeter thick insulation. So R3 is equal to R naught plus T, and that is equal to 4 centimeter plus 4 centimeter, and R3 is equal to 8 centimeter, which is 0.04008 meter. Now there is only one directional radial heat transfer in the pipe. The heat loss per unit length of the pipe is Q over L is equal to Ti minus T naught upon 1 upon 2 pi ln R naught over Ri upon plus ln R3 over R naught over KIL. Now in this particular equation, Ti is equal to 550 degrees Celsius. This is equal to 550 plus 273. It is 823 Kelvin. T naught is 200 degrees Celsius, which is 200 plus 273, that is 473 Kelvin. K is equal to 19 watt per meter Kelvin, and Ki is equal to 0.17 watt per meter Kelvin. So Q upon L is equal to 823 minus 473 upon 1 upon 2 pi ln 0.04 0.02 upon 19 plus ln 0.08 over 0.04 upon 0.17, and Q upon L is equal to, which is comes out to be 54.163 watt per meter. That is the answer. Now the interface temperature between outside tube wall and the insulation can be found as the heat per unit length for overall system should be same as heat transfer per unit length of this interface. So again, coming back to the figure, this is T naught, this is R. Now Q over L is equal to T minus T naught upon Ln, R3 over R naught upon 2 pi Ki, and that is 54.163, which is we have already obtained, and that is T minus 473 upon Ln 0.08, 0.04 upon 2 pi into 0.17, and that is 54.163. So while calculating, then we got this T is equal to 508.148 Kelvin, and that is our answer. Now let's talk about the second question. Now here, what will be the thickness of insulation if the temperature of inner side is 300 degrees Celsius and temperature at outer side is 38 degrees Celsius. The thermal conductivity of the insulation is K, which is K is equal to 0.57 watt per meter Kelvin, and the inner radius is given as R1 is equal to 0.035 meter. Now if heat transfer per unit length of the cylinder, that is QL, is 60 watt per meter. Now let us solve this particular problem. Now here it is given that R1 is equal to 0.035 meter. We don't have any clue about R2. T1 is equal to 300 degrees Celsius, and that is equal to 300 plus 273, and that comes out to be 573 Kelvin. So let's draw the figure first, that is R1, R2, T1 and T2. So T2 is equal to, it is given that 38 degrees Celsius, so 38 plus 273, it comes out to be 311 Kelvin. Now the heat transfer per unit length of the cylinder, that is Q over L, is equal to 60 watt per meter. So we know the heat transfer per unit length for cylinder. So Q upon L is equal to T1 minus T2 upon 1.2 pi Ln R2 over R1 upon K. That is equation number 1. The thermal conductivity of the insulation, that is K is equal to, which is given at K is equal to 0.057 watt per Kelvin. Now if we substitute these values in this particular equation, we will have 60 is equal to 573 minus 311 upon 1 upon 2 pi into Ln R2 over 0.035 upon 0.057, and this is Ln R2 over 0.035 is equal to 262 upon 60 into 2.793, and R2 is equal to 0.035, that is equal to e to the power 1.5634, and R2 comes out to be 0.161713. The thickness of insulation will be R2 minus R1, and that is 0.16713 minus 0.035, and that is 0.13213 meter, and that is our desired answer. Now let's talk about the heat transfer in spherical insulating material. So first in this category is the spheres. So let us consider a sphere. This is the sphere of inside radius is given as Ri, and outside diameter or radius is given as R0, and taking a small element of any radius, and that is dr, this one, for calculation as per this particular figure. Now if T1 be the temperature at the inner part of the sphere, and T2 be the temperature of the outside surface, then assume that T1 is greater than T2, that is a pi flow. The rate of heat flux according to the Fourier law is given as Q is equal to minus K 4 pi r square dt over dr, where A is we can write at A is equal to 4 pi r square, and that is the area of heat transfer. K is the thermal conductivity of the spherical material. So if we rearrange this particular equation, then we will have dr over r square is equal to minus K into 4 pi upon Q dt. So let's adopt the boundary condition. R is equal to R1 and T is equal to T1, and R is equal to R2 and T is equal to T2. So if we integrate dr over r square from the limits R1 to R2, then it is equal to minus K into 4 pi upon Q integration from T1 to T2 dt. Now after integration and putting the values, we have Q is equal to T1 minus T2 over 1 upon 4 pi K into 1 upon R1 minus 1 upon R2. Or conduction heat transfer through a sphere can be written as Q is equal to T1 minus T2 over 1 upon 4 pi K into 1 upon R1 minus 1 upon R2. Now it is the ratio of temperature difference to the thermal resistance to heat transfer between the radius R1 and R2. Or you can write as Q is equal to 4 pi R1 R2 K into T1 minus T2 upon R2 minus R1. Now where Rm is equal to square root of R1 R2. This is the mean radius or geometric mean for a sphere. So if we write this particular thing into this equation, it can become the Q is equal to 4 pi Rmk into T1 minus T2 upon R2 minus R1. Now let's discuss another problem which is related to the spherical issue. Now if a spherical ball of steel of inner radius 2 centimeter and outer radius of 4 centimeter is filled with hot matter, and the temperature of it was say 275 degrees Celsius. The thermal conductivity of the steel is 7.68 watt per meter Kelvin. Now if it is exposed to ambient temperature 25 degrees Celsius, the heat loss would be calculated, and the convective heat transfer coefficient is given as 0.20 watt per meter square Kelvin. So let us take this problem. So this is your sphere where we are having the R1, R2 and T1, T, and this one is K, and H0 and T ambient. So this is a sphere. Now it is given that R1 is equal to 0.02 meter, R2 is equal to 0.04 meter, K is sphere is equal to 7.68 watt per meter Kelvin, H naught is equal to 0.20 watt per meter square Kelvin, T1 is equal to 275 degrees Celsius. So if we convert it into the Kelvin, it needs to be added with 273, and then T1 comes out to be 548 Kelvin. T ambient is equal to 25 degrees Celsius. If 25 plus 273, it comes out to be TA is equal to 298 Kelvin. Now the heat transfer from inner surface at T1 to the outer surface at T will be through the conduction, and from out surface at T to ambient TA will be transferred by the convection. So both will take place simultaneously. So let us write the equation T1 minus TA upon 1 upon 4 pi Ks into 1 upon R1 minus 1 upon R2 plus 1 upon A naught H naught, and that is equation number 1. Now A naught is outside surface area of the sphere, which is equal to 4 pi R2 square, which is equal to 4 pi into 0.04 square, and A naught is equal to 0.02011 meter square. Now if we substitute all given values in given equation, then Q is equal to 548 minus 298 upon 1 upon 4 pi into 7.68 into 1 upon 0.02 minus 1 upon 0.04 plus 1 upon 0.02011 into 0.20, and that comes out to be Q is equal to 0.998 watt, and that is our desired answer. Now let's talk about the optimum thickness of insulation. Now it can be obtained by economical approach. On increasing in the thickness of insulation, there is a reduction in the loss of heat, thus saving in the operating cost, but at the same time the cost of insulation will be increased with increase in the thickness. The optimum thickness of insulation is one on which the total annual cost of insulation is minimum. Now here you see that the optimum insulation thickness. Now here the total annual cost and the thickness of insulation. So you need to find out the optimum value based on the fixed charge and the value of heat loss, and this is again a well known phenomenon. Let us talk about the critical thickness of insulation for cylinder. Now for the insulation on the external surface of the pipeline and the vessel to reduce the heat loss to the ambient temperature, and that is in the steam piping carrying the refrigerant, etc. So the greater insulation will result in less in heat loss, which always not be true. So let us consider a long cylinder pipe carrying the steam at T1 of the inner radius R1 and outside radius R2. It is wrapped with an insulating material of the thermal conductivity K2 to a radius R3. So let heat transfer coefficient at this radius is H naught. Now HIB, the heat transfer coefficient at the inner surface, which is as reflected in this particular figure. Now the rate of heat transfer can be given as Q is equal to 2 pi L into Ti minus T naught over 1 upon R1 Hi plus ln R2 over Ri over K1 plus ln R3 over R2 over K2 plus 1 over R3 H naught. So let Q be the function of R3 and the other parameter being kept constant. It will rise up to a maxima of a certain value of R3, and the value is called the critical radius of insulation. So if we simplify this particular equation, we will have Q is equal to T1 minus T naught over 1 upon 2 pi L into 1 upon R1 HI plus ln R2 over R1 over K1 plus ln R3 over R2 over K2 plus 1 over R3 H naught, and by this way we can calculate the R total, and that comes out to be R total is equal to 1 upon 2 pi L into 1 upon R1 HI plus ln R2 over R1 plus over K1 plus ln R3 over R2 over K2 plus 1 over R3 H naught. So all the parameter in the last equation, they are constant except R3, which is depending upon the thickness of insulation and required for minimum amount of heat transfer. For minimum value of critical radius of insulation, it can be obtained on differentiating this particular equation and put equal to 0. So by this way, if we substitute all these things, it can become R3 is equal to K2 over H naught is equal to RC, where RC is the critical radius of insulation. So by this way, you can calculate the critical radius of insulation. Now the last equation is the critical radius of insulation for the cylinder. Now if the critical radius of insulation is greater than the outer radius of the pipe, then adding insulation up to RC will increase the heat loss from the pipe. The addition of the insulation thereafter will reduce the heat loss from the pipe. When the critical radius of insulation is less than or equal to the outer radius of the pipe or container, then addition of insulation will immediately reduce the heat loss from the pipe. Now this is the figure which reflects the relationship in thickness of insulation and Q and R3. Now let us talk about problem. Now here the problem statement says that what will be the critical radius of insulation for material that is asbestos in this case, where K is equal to 0.20 watt per meter Kelvin, surrounding the pipe and exposed to the room temperature at 25 degrees Celsius with H naught is 2.5 watt per meter square Kelvin. Now you need to calculate the heat loss from a 230 degrees Celsius of 60 millimeter diameter pipe when covered with the critical radius of insulation, and without insulation. Would any fiberglass insulation having the thermal conductivity of 0.03 watt per meter Kelvin cause decrease in heat transfer? So let us solve this problem. It is given that K for asbestos is 0.20 watt per meter Kelvin. H naught is given as 2.5 watt per meter square Kelvin. T naught is given as 25 degrees Celsius, and that comes out to be 273, that is equal to 298 Kelvin. Ti is equal to 230 degrees Celsius, and that is 230 plus 273, this comes out to be 503 Kelvin. Now we know the critical radius of insulation for the cylinder is given by RC is equal to K upon H naught. So RC is equal to 0.20 watt per meter Kelvin upon 2.5 watt per meter square Kelvin, and RC is equal to 0.08 meter. That is one answer. Now the diameter of the bare cylinder, now here you see now the diameter of the bare cylinder is given as R1 is equal to 60 mm upon 2, and that is equal to 0.03 meter. Now heat transfer with insulation, that is Q over L is equal to 2 pi Ti into T naught Ti minus T naught upon ln RC over R1 upon K plus 1 over RC over H naught. And if we substitute the value 503 minus 298 upon ln 0.08 over 0.03 over 0.20 plus 1 upon 0.8 into 2.5. Now upon solving, it comes out to be Q over L is equal to 130.05 watt per meter. Now without using insulation, now the heat will flow through the outer surface of the bare cylindrical pipe to the ambient atmosphere. If you see here, it will go to the ambient atmosphere at 25 degrees Celsius. Now this is a case of convective heat transfer. So in that case, we can write 2 pi r into H into T naught minus Ti, which is 2 pi into 0.03 into 2.5 into 503 minus 298, and that comes out to be 96.604 watt per meter. Now the percentage increase in the heat transfer that is equal to Q heat transfer with insulation minus Q without insulation over Q without insulation multiplied by 100, and that is 130.05 minus 96.604 divided by 96.604 into 100, and this comes out to be 34.622%. That is the answer. Now if given fiberglass insulation, then K is equal to 0.03 watt per meter Kelvin, and the critical radius of insulation RC would be K over H, and that comes out to be 0.03 upon 2.5, which is equal to 0.012 meter. Now the value of RC is less than the outside radius of the pipe, and that is 0.03. So addition of any fiberglass insulation would cause a decrease in heat transfer. So that is the issue. Now let's talk about the critical thickness of insulation for spheres. For spheres, the heat transfer equation can be written as this particular equation, and when we talk about the R total, this can be written as this particular equation number 2. Now let R1 and R2 are the inner and outside diameter of the sphere, and R3 be the outer radius of the insulation, and R2 can be considered as an inner radius for insulating material. So if we differentiate the above equation for R total with respect to R3 and taking all the parameter constant and put equal to 0, then we have this R3 is equal to, our critical radius of thickness is equal to R3, and that comes out to be 2K2 upon H naught. So this equation, this particular equation gives the critical radius of thickness for the sphere. Now where K2 is the thermal conductivity of the insulating material and H naught is the convective heat transfer coefficient for the insulating material. Now let us discuss about another problem. Now if a sphere of inner diameter having 40 mm having the inner temperature Ti is equal to 200 degrees Celsius is surrounded by insulation, the thermal conductivity of the insulating material K is 0.017 watt per meter Kelvin, and the sphere is exposed to ambient atmosphere at 30 degrees Celsius temperature with H naught is equal to 0.20 watt per meter square Kelvin. Then you need to calculate the heat loss with and without the insulation and the percentage increase and decrease in the heat loss and the critical thickness of the insulation. So let's solve this particular problem. Now here the radius of a sphere is given, R is equal to 40 mm upon 2 is equal to 20 mm. Now here Ti is equal to 200 degrees Celsius, which is equal to 200 plus 273, that comes out to be 473 Kelvin. Now if sphere is surrounded with the insulating material, then Rc is equal to 2K upon H naught, which is 2 into 0.017 watt per meter Kelvin upon 0.20 watt per meter square Kelvin, and Rc is equal to 0.17 meter. That is the first answer. Now T ambient is given as 30 degrees Celsius or 30 plus 273, that comes out to be 303 Kelvin. So the rate of heat transfer in a sphere with insulation, that is Q is equal to Ti minus T ambient over 1 upon 4 pi RRCK into RC minus R plus 1 upon 4 pi RC square H naught, and that is 473 minus 303 upon 1 upon 4 pi into 0.02 into 0.017 into 0.17 into 0.17 minus 0.02 plus 1 upon 4 pi into 0.17 into 0.2, and the Q comes out to be 0.7717 watt, and that is the answer. Now the heat transfer in a sphere without using insulation. So Q is equal to H naught A into T I minus T ambient, which is H naught into 4 pi R square into Ti minus T naught, and that is 0.20 into 4 pi into 0.02 square into 473 minus 303, where H naught is equal to 0.20 watt per meter square Kelvin. Ta is equal to 30 plus 273, which is equal to 303 Kelvin. So Q is equal to 0.1709 watt. Now the percentage change in the heat transfer with or without using insulation. So this is Q with insulation minus Q without insulation upon Q without insulation, and that comes out to be 0.7717 minus 0.1709 upon 0.1709 into 100, and that is equal to 351.55%, and that is our desired answer. So in this particular lecture, we discussed about the various aspects of heat transfer, insulating material, and solved and we discussed the various cases like cylindrical aspect and then spherical aspect. For your convenience, we have included couple of references, and if you wish, you can have a look of all those references for further study. Thank you very much.